Hello and welcome to the third day of our third School of the Assumptions of Physics. Today we are going to look at open problems. As we said before, we want to run the Assumptions of Physics program as an open research project because we require competencies from many areas of physics, math, and philosophy, and so we need to sort of pool competencies from different sides. So today I'm going to go through some of the open problems that we have. First in reverse physics and then in physical mathematics. And if people are interested in joining and contributing, you can send me an email or at info@assumptionsopphysics.org, and so that I can send you an invite to the Discord server, which is where we collaborate and we sort of keep track of what we are doing. Last year we also did a reading group which is available in this channel. We're trying to have discussions which will resume at some point on Saturdays, and so if people want to participate, those are good ways to start seeing what's going on and participating. Okay, so let's start with open problems in reverse physics. Let me check. No, this of course is not working because I am live, and of course things should not work when I have. My mouse has stopped working. That's nice. My keyboard has stopped working. Oh, that might be a problem. Yes, completely. Okay, so now I have, let me try, if I do this, that's gonna destroy completely everything. Okay, so of course problems have to come exactly right now. Let me try to fix them. Okay. Is this going to work? No, even worse. My docking station is completely not working now. Ah, great. Well, I think I have to restart my computer. So I'll be right back. Christine, you can take it from here for 1 second.
Okay, if we need to, you can also I can get the slides from you and I guess change them if your audio and video are working fine, but I'll let you try to reboot
Yeah, and
for.
my whole setup is not working, so I don't
Yeah,
even know
okay.
what's gonna happen with the stream and everything. Everything is not working. So
Okay. Your video is frozen. We still hear your audio.
great. It's completely. I can't even turn it off. All right, let's do this.
It looks like you successfully got out at least. We'll give him a couple of minutes. Thanks for your patience. anybody happens to have questions based on the material that's been presented over the past couple of days, they can feel free to ask them if they'd like, since we're waiting anyway. Try to download the slides in the meantime in case sharing them from my side ends up being useful. Also put okay, we have a question in the Q&A. Will we be overviewing all open problems, or are we only covering a select few? I doubt we'll have time for all open problems, but I don't think it'll be a deep dive on only a few, so it should be a fair number, but I don't think it'll be all of them. I can put first, everyone can put to the website where all the materials are posted. So the slides from the past few days are posted on our website already. I just put that in the chat. So it should be visible to everyone. Download slides for today locally. Okay. Could someone confirm that you can see the link to the slides or the school website? Either with a reaction or a response from the Q&A. Yes, okay, very good. And for those who just joined, Gabriel's having computer problems. He was here earlier, and everything worked before 10. He even had his slides up and things that he tested, and somehow his computer stopped working. So we are waiting for him to rejoin. Jamie elsewhere. Okay. There he is.
Alright, now I have to check that all the everything is still working. Of course, it has to happen when I am presenting. Like everything updated, the Zoom updated in the meantime, all the things. Okay, so is the live still working?
Oh,
That, yes. Okay. Okay, so now I can finally start. Sorry about that. Completely be beyond my control. And these are the slides, and my cursor is working. Okay, so let's start. Okay, so first thing that needs to be done, or that I'd like to do in reverse physics, that I'd like some help, especially on the philosophy side, is basically to streamline the methodology. So a lot of the things that we've done in classical mechanics were kind of ad hoc. What happened is that when I started doing quantum mechanics, it kind of a little bit more formal, because all the issues or the mathematical the math does not quite map to the physics well, and so we need to sort of tease out which pieces of the math are correct or not, so that that means that we have to have a finer sample. And I really like to make the methodology as much as possible close in the language and style to reverse mathematics, so that it looks similar in some way. And so the one of the goal would be also to then reformulate all the results that we have from classical mechanics under the new standard, so that we can start playing around with the standard. And again, the idea should be to really formally define what it means to do reverse physics, so that if somebody comes outside and says, I have a theorem that I think it's reverse physics, this is how you package it so that it follows the style, and every time that somebody comes and looks at reverse physics results, sees sort of a similar style that sort of feels that it's within the same product. So as I was saying before, to compare and construct reverse physics and reverse mathematics, there are similarities in the sense that the idea is to study the discipline by understanding which part of math and physics are responsible for what result, and this is very similar in spirit. When I talk to people who did reverse mathematics, they would recognize that this is what we're doing. And then another thing that is similar is that we want to find results that connect with well-established structures in the literature. So we don't want to develop, a 400 pages framework that somebody has to buy in to be able to understand anything, because we want to be able to take insights out of reverse physics and make it applicable to teaching, to other people that are doing research in math and physics, to sort of push forward the research. And this is again something that I learned that a lot of people who works in reverse mathematics do. They try to get some of the result and then find collaboration with other people to sort of explore it. The difference is, of course, is that reverse mathematics is very focused on representation and computability, so the techniques that they actually use are completely not applicable to reverse physics. And also reverse physics cannot be limited to the formal system, because we need to talk about experiment, what happens in the real world. And so there are issues that are not formal. So we talked yesterday about test and verifiability. What does it count for a test to be verified? What does it mean that something is true? All these things cannot be inside the formal framework, but they're kind of important for us, and they need to be discussed, but they're not going to be part of the formal framework. So one of the things that we're trying to do is the idea that everything is a condition, and you find relationship to conditions. So the way that things have progressed in the foundation of mathematics, some things are called axioms, some things are called lemmas, some things are called theorems, even though you can find equivalence between these things. And so it's kind of weird to say that an axiom is equivalent to a lemma. So what we basically want to say is we just have conditions, and then you prove equivalence or relationship between these conditions, so that what acts as an axiom and what acts as a theorem can change depending on which are the conditions that you presuppose, right? So the idea is really to write these conditions in the following way, each giving a name, and the name is all caps, which kind of follows what in reverse physics do. And ideally, we would like to have the same name used to identify the same condition within the field. So we would like to basically form a database of these conditions and you know, and then map all this logical relationship. I've even toying with the idea to have a website in which you can search these conditions and then you pick one conditions and you find all the relationship between all other conditions. Like something like that can in principle be done. Then the idea is that some conditions form, I don't know how to call it yet, a cluster of conditions that are essentially related by logical equivalence. And what we do here, for example, is in quantum mechanics, you have that the Schrödinger equation is equivalent to information preservation. So we put a prefix to be sort of the group, the cluster of conditions, and then the same conditions can be implemented in different way. So let me do this because where is it? Our options visible. There you go. Otherwise the cursors disappear and annoys me. And so again, the identification of what these clusters are and how to name them, it's something that it's somewhat open. And then we want to find base conditions. If you remember, there is this idea that we want to find a base theory for all of physics, which is the set of conditions that are, they need always to be valid in any physical theory. And right now I have this idea of mark the condition with this B at the beginning, saying that these are conditions that have to be true because otherwise the physical theory does not make sense. And again, the idea is to make a collection of all this so that also when we do physical mathematics, we have an idea of what are the things that are starting points that we must have. And then we want to be able to have standard naming for relationship between conditions. So we can say that A implies or requires B over T. So T is going to be our base theory, and A or B are two conditions. And then if A implies B over T, it means that A and T implies B. And once T is assumed, if A is true, is B is true. And so the idea is that these are sort of all the possible, I think, conditions that you can have. You can have that A excludes B over T, meaning that if A is true, then B is false. A is equivalent to B over T. Once T is assumed, A is true if and only if B is true. A is independent of B because neither forces the other, so you can assume A and you don't know what B is. You can assume B, you don't know what A is. You can say the two conditions are consistent, meaning that they can both be true once T is assumed, or they're inconsistent, that if you take one, the other one can't be taken as true, so they can't be true at the same time. So these are the type of things, ideas that I'd like to formalize at some point. It would be nice to have sort of a well thought out paper, chapter in the book that spells out all these things, that gives some example. So if somebody comes into reverse physics, says he sort of can understand how the thing work, and then we can revise a lot of results based in according to this standard. And this is kind of what I started to do. If you have been seeing in the last few months, I've been writing these technical briefs that try to spell out results with this format, and I basically did it to try out whether this works or not, right? So the methodology has to be useful. It's not that descends from above. We need to try it out, see if it's useful, see if it's convenient, and then tune it based on that, so that we can find something that is comfortable and nice to use. So that's sort of for the overall methodology, and of course there are the different theories that we have been looking at and what is the status. So classical mechanics is essentially done, though things can be improved, especially if we want to make the methodology tighter and close up some possible loophole around. Quantum mechanics is something that I've been trying to work on it for the last year, but I've always been distracted with other things. But there is already a lot of work that it's been done. We basically need to just clean up a lot of results. And thermodynamics is something where we have, again, a lot of ideas, in some sense, probably even better developed than quantum mechanics, but it's been in the back burner for, I don't know, 3 years now. And field theories are really things that we're not touching right now. It'd be nice to have some people that help me sort of at least to work on the classical side so that we can start at least having ideas of what exactly needs to be done, because we just have ideas of how things should be, but we don't know how to actually implement them. So for classical field theory, so let's start from there. So again, as I said before, I'm looking for somebody to help generalize the results that we have from classical mechanics to field theory. And the main conjecture, as we see, is that the volume in space provide a count of degree of freedom in the same way that the symplectic form gives us the count of configurations for each independent degree of freedom. And to be able to pull this off, we need to find a suitable Hamiltonian symplectic formulation of field theory that sort of connects and generalizes the idea that we already have. We have to understand how to generalize the count of states, the entropy, and so on to fields, and then adapt the arguments from classical mechanics to field theory. Ideally, the argument should be the same, right? There is this passage from mechanics to fields where you change position to be the number of degree of freedom, the index for the degree of freedom to the position. Like these type of things should actually work because the physics works that way. The math does not quite work that way, and so we have to understand how to make everything work. And there is an issue of units, as usual, that needs to be understood that doesn't usually work. So what we think about, just to give you a sense of how we think that this whole thing generalizes, you saw this slide from the first day. This is the idea that the principle of least action is essentially telling us something about the flow of states, that the variation of the action is just the flow of states. And so these are the type of things that we need to generalize. If the action is the line integral of the vector potential, we need something like that for field theories so that we know what the Lagrangian density is, we have Hamiltonian constraint for there as well, and we can interpret the conjugate pairs as forming these degrees of freedom as well. So just to give you a sense of how, in my mind, things progress. So suppose that we start with the discrete case, and we have two variables, Q1 and Q2, and Q1 is the shape, and Q2 is the color. So if you want to know how many possible configuration you have on the Q1 variable, which would be this set, you basically go and count. I have 3 possible shapes, so the count of configuration is 3. If you now take a volume, a possible states, not just configuration of one variable, then whatever set you have, you just go and count the elements. So V has 4 elements, so the count of possible states in the set is just 4. And if you want to count the degree of freedom, you just count them. They're discrete to 1 and 2, so this would be 2. So this is how counting works in discrete case, and it's very simple. In the continuous case, it's not as simple, because as we saw before, changes of variable would change the count, so we need to have a way to make this count invariant, and the symplectic form, the idea of conjugate variable is what works. So we have this line represents the first degree of freedom, this line presents the second degree of freedom, this S represents a surface, and so now we want to know what is the count of configuration along S. and we just integrate with the symplectic form, which basically you can think it as a density of configuration. So for every little area, the symplectic form tells us how many configurations you have, you integrate, and you get a value. For the number of states, what you basically do is make the product of every along independent degrees of freedom, and so you make the wedge product of the symplectic form with itself, which basically you are going and look at the volume, and you go and calculate the Liouville volume, Liouville measure, which is the count of states. Now note that the points here, both for S and V, are infinite, right? But we don't say that we have infinitely many states. We have the states counted as the symplectic measure. So we went from a counting measure to the Liouville measure here. So this is how we make the transition from a discrete to continuous. We change the measure. We change how things are counted, but the degrees of freedom are still discrete. We have 2, 3, 4, n degrees of freedom. So the measure that we use for the number of degrees of freedom is still the counting measure. And so the idea is that in field theory, you have a degrees of freedom for each point in space. And so the degrees of freedom themselves are continuous, are dense. You have infinitely many, and therefore we can't count the degrees of freedom with the counting measure because we just would have infinity, which do not make much sense. So the transition between all this framework to field theory would basically need to fix this so that we know how things work. And so the conjecture should be that general relativity should be just the deterministic and reversible evolution plus the degrees of freedom independence for infinitely many, for densely many degrees of freedom. So we have a continuous of degree of freedom at each point, and each point we have configurations, and then the product of all the possible configuration at all points gives us these volumes that then we have to go and count the states. And so, in the same way that our Lagrangian here is related to some count of states, we would like to say that the Lagrangian density is giving us some flow of states. So the Lagrangian density kind of needs to give us a count of configuration per degree of freedom. That's the physical meaning that I'm pretty sure it's going to work. It's just that we don't know how to do it. And the conjecture is that the volumes in space represent the number of degrees of freedom, because if I have a volume, right, and I double it up, I'm doubling the number of conditions that I'm giving you, therefore I'm doubling the number of degrees of freedom. And the idea then should be that when we write our Lagrangian density, there is going to be a part that tells us how the flow of configuration is changing, and one that is responsible for the flow of degrees of freedom. And so if the number of degrees of freedom or the density of degrees of freedom changes, then of course the density of configuration is going to change, and if we have deterministic or reversible motion, these two things have sort of to change in sync so that the total number of states is conserved. It's a little bit of an intuitive way to see it is that in a field theory we are mapping values between Cauchy surfaces, and the degrees of freedom are the points at the Cauchy surfaces, and the number of configuration are the possible field values at each point. So if you imagine that your Cauchy surface is stretching, it's like the degrees of freedom are getting farther apart, and if the degrees of freedom are getting farther apart, then the configuration density is also going to change, such that the total number of states is conserved. So this is the intuition. I'm pretty sure that it's correct intuition. I don't know how to pull it off mathematically to show, oh, this is how the intuition maps to the math. And again, if people are interested in this, we can have more of an in-depth live discussion. We had actually one a few weeks ago, but if people want to join in and try to figure this out, I'm able, I'm willing to talk about this to death. So since we are a little bit behind because of the snafu, I'll try to go quickly. For thermodynamics, again, wait. Okay, that was a wrong. So for thermodynamics, we basically have, we think we have identified the key idea, and essentially the physical entropy, it's not the logarithm of a count of states, but of the count of the possible evolution and the fluctuation. And this gives us the correct notion of equilibrium. And an equilibrium dynamics of the system does not, equilibrium means effectively that the dynamics of the system does not depend on the internal dynamics and the environment and the dynamics of the environment. This is kind of what we talked a little bit, what Christine talked about as one of the big four in reverse physics, the idea that you need need a notion of equilibrium to sort of separate the system that you want to study from everything else. So let's quickly go through and see how this idea works, which again, it's in the preliminary phase. The math needs to be developed, but it's very promising, as you'll see, because it gives us a result in a very straightforward way. So let's start in saying that we have a system, and this is the space, the state space of the system. So these are the possible states. And then, of course, you're going to get a copy of that state space at a different time. And then you're going to have a process that this system is going to undergo. And an evolution is the complete description of the system at all times. So if I told you this is the evolution, I told you what state is, what the state of the system at each moment in time. And so now a process defines of a set of possible evolutions. So if we have a damp harmonic oscillator, we know that in phase space our system is going to spiral, and those are the possible evolutions. So I can give you the set of all the possible evolution instead of giving you the set of equations, and that corresponds to essentially describing the process. Note that in general, a process might, for a process, one evolution might be the same for some times, and then sort of, depending on random event, things can branch out, rejoin, and so on. So this is a completely general way of telling you what the process is. Now, each description at each time corresponds to a set of evolutions. So if I tell you that at time t I have this state, then I know that the system has to be in one of these two possible evolutions. These are the two things that the system can do if I told you that the system in this state. And so the idea is that we are able to count the number of evolutions for a particular state at a particular time with some sort of measure. It might have to be more complicated than a measure, but that's basically the idea. We give it a set of states, and you tell me what are what is the number of evolutions that are compatible with that state. So this is basically one of the things that we impose, that we say we are able to do. What is interesting is that just by knowing that we have that measure, we can define conditional probability. So the probability of having S1 at time t plus delta t, given that I have S0, is just the count of evolution that go through both divided the count of evolution that goes to S0. So the point is that you get automatically a notion of probability just by saying, I know how to count of evolution. And this is kind of similar to some of the things that one does in stochastic processes. So at the end of the day, this is it's compatible with a lot of math that is out there. Now, a process is deterministic if knowing the state at a time allows us to predict the state of the future. So if I am here, I'm going to be here. If I'm going to be here, I'm going to be here. So these are the processes for which we can write a law of evolution. We can say that the state at time of t plus dt is a function of and only of the state at the previous time. So if we want to write laws of evolution, you are assuming this. So that's kind of an implicit assumption when we have a lot of evolution. Now, in a deterministic process, you will note that the evolution can never split, because once I know that I'm here, I must have only one possible future state. So the evolution can never split, and they can only merge. Therefore, if we go along an evolution and we look at the count of evolutions per state as we evolve, this can only increase or stay the same, because, again, evolution can never split and only merge. Now we can say that a process is reversible if knowing the state at a time allows us to reconstruct the state at a past time. This is essentially the dual, like we're just inverting the direction of time for our definition. And so in a reversible process, the evolution can never merge, they can only split, because if I'm here, there has to be only one state that I'm coming from. So the count of evolution as we evolve can never increase, can only decrease or stay the same. And so now if I have a process that is deterministically reversible, then our count of evolution has to remain the same, because evolutions can never merge and can never split. And so we have this idea that for a deterministic process, the count of evolution can only increase or stay the same, and it's equal if it's reversible. And this kind of already sounds like something like an entropy. And now consider a process where a system reaches a final equilibrium that can be predicted from the initial state. So I start here, I go to an equilibrium, and then I always stay in the equilibrium. And at equilibrium, evolution cannot merge anymore, so they have to stay the same. So that same quantity that we have not only cannot decrease during the deterministic process, but has to be maximum at equilibrium. So again, this sounds like an entropy. But an entropy has a particular property when you join independent systems. So we have to understand how the count of convolution works when we have composite systems. Now, the state space, if you have two systems, is always the product. You have a state on one, you have a state on the other, there's going to be some notion of product. In quantum mechanics becomes a little bit more complicated, but at the end of the day, once you know the two original states, you have a notion of product that's going to be the correct one. And the count of configuration here is going to be the product of the two. But the evolution in general are not the product, because if we have these three possible evolution for x, these three possible evolution for y, when we make the joint evolution, you see that we have a correlation, and so the total number of evolution on the joint system is not the same. It becomes the same when the systems are independent, meaning the violation of one does not constrain the evolution of all possible pairs. So in that case, each pair of evolution, there is an evolution of the composite, and therefore we can say that the measure becomes the product. So the count of evolution on one, on the joint, becomes the product of the two counts of evolutions. And this is the conditions that tells us we have a system independence through time, the fact that the evolution factorizes. And since we want our entropy to be additive, and the logarithm of the product is the sum of the logarithm, we can see that the logarithm of the count of evolution is additive for independent system, and therefore we can define a process entropy as the logarithm of the count of evolutions. It is additive for independent systems, so if 1 and 2 are independent, the process entropy will be the sum. And since the logarithm is monotonic, we still have the property that we had before. For a deterministic process, the entropy increases or stays the same, it's equal if it's reversible, and it's maximal equilibrium. And so the cool thing is that we had made absolutely no claim of what the systems are. And now the question is whether this is at all related to the standard notions of entropy that we have both in information theory and in thermodynamics. Now, how do we recover the information entropy? Now, suppose that x is a macrostate, which is a dynamical equilibrium of microstates. So if we, and macrostate, we're going to have some variable, but if we zoom in, the system is evolving according to some lots of possible dynamics, and it's going to do something, but it's in a sense in equilibrium. The microstate fluctuation can be characterized by a stable probability distribution ρ for each small delta t. And an evolution lambda t for the microstate is a dense sequence of infinitely many microstates whose recurrent matches ρ. So you can imagine to get the dyadic numbers within your delta t, you get 1/2, you get 1/4 and 3/4, and so on. You make this dense countable sequence. You assign an element from a probability distribution that becomes one of the possible fluctuation, one of the possible evolution for the microstate that is consistent with the macrostate. And the idea is that the microstate measurement cannot be sensitive to these permutations of the microstate. So the possible evolutions that are consistent with the microstate is basically all the possible permutations. And the Shannon entropy exactly counts all possible permutation of an infinite sequence that is dense in delta t, which equals all possible evolution. So we have a way, with the notion of equilibrium and statistical evolution, to recover the idea of the Shannon entropy used to count microstates and all of that. This all works. So the idea then is that the macrostate, the equilibrium, is kind of a tube, right? And we always study the tube without even knowing what the microstate is doing. So the equilibrium means that no evolution enters or exits the tube, right? You're always in sign, so because external agents have equilibrated, so you're always staying in the tube. And the variable described in the macrostate can still change, meaning the tube moves around in state space, but the microscopic dynamic remains, all the fluctuation still remain inside the tube. And we can study the tube as it were a single line, because from afar this fluctuation will look small, they're not going to change our x, and so we're going to think it as a single line. And so again, we have this notion of equilibrium as that the evolution is decoupled from the environment and from the internal dynamics. We can just study the properties of the macrostate of this tube without caring what happens during those fluctuations. And of course, if this fluctuation go out of the tube, then this fluctuation would have effect at the macroscopic level, because our macrostate would change, and that would be exactly when we can't use that notion of macrostate anymore, and we would have to go and look for something else. So this sort of is the core idea, and it seems to hang together decently. And note that we have not mentioned uncertainty, disordered statistical distribution, information, lack of information. All of those things don't seem to be relevant. We have not discussed what type of systems we have. It could be a classical system, a quantum, biological, economic system. All the things that we have are independent, and this sort of would tell you why ideas from thermodynamics are actually used in ecology, economics, biology, and lots of other places. And the other thing is that the process entropy increase is explained by the definition and the setting. You were studying processes that are deterministic, rules for which we can write law. In that context, we can define this process entropy that has this nice property. So the explanation is really very straightforward from the definition, and it's not mechanical. Like the mechanism, the particular mechanism is completely irrelevant. All the explanations are definitional. And I think these are the type of explanation that we do want to have in a foundational theory of physics, because if you try to use mechanism to explain, you always need to require a lower level that tells you what the mechanism is, but then how you're gonna justify that lower level with another mechanism, and so you have this never-ending descent of turtles all the way down, and you never stop. While if it's definitional, I have a system that obeys these assumptions, and everything starts from that, then you have a nice starting point, which is typically the same starting point that you have in math. Your axioms are essentially your operative assumptions for what you want to do, and then you build things up. So it gives you a much more tight-knit story. So this is all open, and there is also a sense that then we can recover the standard thermodynamics by going through essentially what Gibbs did. If you assume the states are equilibria of faster scale processes, and you assume the states are identified by extensive properties, and one of them is the energy that is conserved under closed system, then you have an equation of state, and from the equation of state you can define the intensive variable through derivation, and then the key thing is that you want to study the interplay of changes of energy and entropy. So heat is an exchange of energy that is only that it's all given by a change in entropy, while work is exactly a change of energy that makes absolutely no change in entropy. And the division of work and heat becomes just from that, and you can define reservoir and mechanical systems based on these ideas, and then you can recover the first law and the second law, and you can do everything. So we kind of have these ideas. They have never been so developed so much because we are distracted with lots of other things, but if somebody wants to work on these ideas so that they can fit with the rest of the framework, that's certainly a possibility. Okay, very quickly, because I lost a lot of time in the beginning, for quantum mechanics, it's clear that the irreducibility, the lower bound of the entropy, is the only ingredient that makes quantum mechanics different from classical mechanics, and that's now we have to make that work as best as we can. We finally found a way to disentangle the math, and we're gonna see it in the following slide, and we basically need to pull all these things together, find the right math to do it so that we can do it. So the main idea, again, is irreducibility, the idea that a classical system can be understood as made of parts and parts and parts, and we can track all the parts. And in a statistical way, you can think of having a probability distribution that you can keep divided into finer and finer and finer probability distribution, and where the limit is your point in phase space, which is a delta Dirac. And while you're doing that, you're assuming that there are probability distribution with lower and lower and lower entropy, and that's basically where the assumption comes in. You are assuming that you can prepare ensembles at arbitrary low entropy so that you can study these macroscopic infinitesimal parts, and you're assuming that you can always have access to the internal dynamics. You always can tell that this piece maps to this piece regardless of how you make that sphere small. In quantum mechanics, instead, you want to say, oh, I have a lower bound. I cannot I cannot prepare things as best as I can. There is a lower limit that physically can be thought as I always have interaction with environment that does not permit me to prepare everything as I want. So I have to choose which quantity I want to prepare well to the detriment of another quantity. So we don't have access to the internal dynamics. At some point we reach some limit that we have a system that has to be studied as a whole, and we can't know what these parts are doing. This already intuitively leads to, in a qualitative way, to some ideas in quantum mechanics. Since you have a minimum uncertainty, you can't squeeze ensembles arbitrarily. Therefore, you have the uncertainty principle, and we saw that we had this in classical mechanics as well. You're going to have a notion of non-locality because now these ensembles are distributed in space, but you can't interact with only one part. So if you decide to interact with this part, well, tough luck, you're going to interact with the whole system, and therefore this gives you a notion of non-locality. But superluminal effect cannot carry information, because being able to know how this information is going through within the quantum system would mean that you can refine the ensemble and therefore you can't do it and therefore you can't extract the information. So you're going to have this non-local effect, but they don't carry information. You can't violate spatial relativity for that. And then you can see that from some symmetry of these idea of equilibrium, you can also get the symmetry of the inner product. But again, I have to skip because I lost 15 minutes at the end. We figured out how to break down the vector space conditions. There are actually three independent things that you could say. If you say the states are rays of a Hilbert space, well, rays don't need the inner product, and they can be just defined on a vector space without the inner product. And it's interesting to note that these do not pick quantum mechanics by itself. So you could have the states are rays of a Hilbert space, but you can still slap on top classical mechanics and classical statistic mechanics, and therefore you absolutely do not have you don't have quantum mechanics. So the fact that you have a Hilbert space and you have rays and all that has nothing to do, well, it's something to do with quantum mechanics because you need it, but it's not sufficient. What is interesting is that once you start defining ensembles as density matrices, this requires the inner product, and this does exclude quantum mechanics, but it does not uniquely recover quantum mechanics. The Born rule is an independent condition from the fact that ensembles are density matrices. So this has finally, we figured this out that allowed us to understand exactly what the pieces of maths are doing, which is the purpose of reverse physics. And now we're starting to write down all these elements well. So if there are people that are interested in going through all these derivations to make sure that what we say makes sense and keep us honest, this would also be useful.
Just to interrupt, sorry, quickly, I think you had a key typo on that last slide. You said it excludes quantum densities, exclude quantum mechanics, but do not uniquely recover quantum mechanics. You meant excludes classical mechanics.
Yes, exclude classical mechanics. Yeah. Okay, then one thing that we want to say about projections, this is the whole measurement problem trying things. We want to say that projections are not unique to measurement, they're just processes, and we want to say that projections are a process of equilibration. A projection mathematically is a linear idempotent operation. The fact that it's linear means that the output of a statistical mixtures of inputs is the statistical mixture of the output, which is a basic requirement that we must have for any process. And idempotent means that if you apply the same process twice, you get the same result. So physically what it means is that you have an incoming state and you have possible outcoming states, and then you redo the same thing and you get the same thing, which means that these states are equilibria of the process. So projections are effectively equilibration processes, and you should think them in a parallel to what happens in thermodynamics. So if I have a cup of water, this is the grand canonical or the canonical, I always get them mixed up. It's the mu Vt ensemble, where it's defined by the temperature, the volume, and the chemical potential that tells you the fluctuation that is happening at the boundary, how many molecules are coming in and out. And of course, the number of particles is not well defined here because it's jiggling around. So now you want to say, but I want a state where the number of particles is well defined. Well, you put a lid, and now you change the type of ensemble that you have, either to grand canonical to canonical, or canonical and grand canonical. I never remember which one is which, and I should have written it down. But the point is that you do not have a mu defined anymore. You have a number of particles defined, and depending on how the fluctuation was going, you are going to have one of the possible outcome, one of the possible end. So the idea is that we want to say that in quantum mechanics, this is exactly what you're doing with measurement. You come in with a particular direction of spin, meaning that your electron is in equilibria with the orientation of your magnets. So you have magnets outside that picks the direction, the electron is there, and then you go through another experiment where you are changing abruptly the orientation of the magnet, and now you're forcing the electron to be in a new equilibrium, which is going to be in a different direction, and it's essentially what you're doing. It's you're going and changing the walls, the boundary conditions. You're forcing the system to equilibrate to the new boundary conditions, and you get your new value. So we want to say that quantum contexts are basically different boundary conditions, and projections are just equilibration processes when you abruptly change the boundary conditions. On the other way, we want to say that unitary evolution is exactly the opposite. You have deterministic and reversible evolution. From the initial state, you recover the final state, and you can go and show that this is exactly the case. And the idea then is that these two things are just two different processes that you use in different assumptions. The fact that something is completely exactly deterministic and reversible, that you have complete isolation, and therefore you can use unitary evolution, the Schrödinger equation, is of course an idealization. It's not true, but we pretend that it's true because it's very convenient. And again, the fact that we have an equilibration process, so that does not depend on anything else. The final equilibrium only depends on the initial state and all that, and it happens instantaneously. Also, that does not really exist. These are just idealizations that we make because they're useful, and in one case we use one, and in case we use the other. What really happens is, of course, a lot more in between, but you know, it's there is no problem with the fact that we have two different laws of evolution because they apply in different conditions. Now, the thing that is interesting is that from one you can recover the other. So you can say that we have processes of equilibration, and you can say that at every moment you are making this equilibration, so you're basically doing a quasi-static evolution. You're changing your equilibria a little bit at the time such that the evolution is smooth. And what is interesting is that you can recover quasi-static evolution from that, and then actually finalizing a much better proof than the one that it's here, that we have no time to go through it anyway. And you can also say the opposite, that projections, this equilibration, are steady state of open evolution. So if you take the Lindblad equation, the equation for an open quantum system, and you set the jump operator to some self-adjoint operator, the steady states are exactly the one that commute with that operator, and so all steady states are statistical mixtures of eigenvectors of that operator. So you can recover projection from the Lindblad equation, which is recovered from unitary evolution. So there is absolutely no sense that these two processes are completely different things that can be recovered one from the other. So you can go from a deterministic and reversible evolution, from equilibration with the environment, I get a black box process with equilibrium, which is a projection, or you can start with the idea I have projections, I make quasi-static evolution, I get unitary evolution. So there is absolutely no inconsistency, and this is the things that we want to, again, develop better inside of reverse physics and make all these conditions explicit and make sure that the math works and so on. Okay, so for quantum field theory, we basically want to wait that we have both classical field theory done and quantum mechanics well done, so that this is going to be it's going to take a few years before we even do that. Some people ask me about quantum gravity, and so I want to say, like in the last 2 minutes, something about that. We're not really aiming to solve this, but the general idea is that if we want to be able to make quantum mechanics consistent with general relativity, we should have a clear idea of what those two things are doing, and then realize what the problem is conceptually, and then try to solve the conceptual problem. So that, I think, we can sort of at least understand what it is. We saw that quantum mechanics is putting a lower bound on the entropy, And gravity, we saw that it should be the proper handling on the count of degrees of freedom. And what one can argue is that a lower bound on the entropy on the count of states cannot be achieved without imposing a lower bound on the count of degrees of freedom as well. So let's see if I have, yes, let's just jump from here. So you can imagine that we had, no, let's go through here. Let's take 1 minute. So the problem of counting in the continuum is the following. Ideally, we would like that every state is a single state. So we would like to say that if I take one state and I ask how many states do I have, we would like to say one. We would also require that when we are in a continuum, a finite continuous ranges carries finite information, and therefore the count of states should be finite. So if I tell you how many configurations there are in 1 kilometer, you shouldn't say infinite, you should say 1 kilometer worth of configuration. It's a finite number. And we would also like the count to be additive for disjoint sets. So if you have two set of cases that are disjoint, and you have X configurations here and Y configurations here, you would like to say that if you take both the whole set, you have X plus Y. And the problem is that these three things are incompatible, and you have to pick two. If you discard the first one, you say points are measured 0, then you have the Lebesgue measure, which is what we use in classical mechanics. The Liouville measure is a measure that says that every state is 0, every single state has, every set with one state has 0 states, which does not make much sense. You can discard the second one, so you say, oh, there are infinitely many configurations in a finite range. Then you get the counting measure, which is what we use in discrete mechanics. Or you can disregard the first one. You basically say my count is not additive. So as I shrink my volume, right, I decrease, but then when I get to the single point, I get 1. And so, of course, the measure is going to decrease, but it's not going to be additive at that point. And so the point is that quantum mechanics, since you want to put a lower bound on the configuration, you want to say that each state counts 1, therefore the entropy of one state is 0, of a single state is 0, then you're putting a lower bound on the configuration on a continuous degree of freedom. And the block ball is still continuous, even though you have two orthogonal states, the possible states on a quantum system is always continuous. And so the idea is that if we want to have a counter configuration to be to have a lower bound, we need to, and we are going to have some counter configuration per degree of freedom, we will need to have a lower bound on the entropy. So the idea is that if we have a volume of space and we say this volume corresponds to a certain number of degree of freedom, right? In classical mechanics, we pick a single point, we would basically be forced to say that at a single point there are no degrees of freedom. And we want to be able to say, no, at a single point in space we have 1 degree of freedom, one possible degree of freedom. And the idea again is that the measure would not be additive anymore. So if you have two distant points, these would be independent degrees of freedom, and so two distant regions are going to be summed and are going to be additive. But if the degrees of freedom are close to each other, then they're very much correlated to each other, and so they do not count as an independent degree of freedom. And so as you shrink your volume of phase space of space, the count of degrees of degree of freedom should go to 1. Of course, we have no idea how to do this. Probably the math for doing this is not being developed yet, but it seems to me that this is the type of thing, given all the other work in reverse physics, that this is what it points to. So the idea is that, again, if somebody is not interested in the current theories and is interested in creating the new one and solving quantum gravity, I still think that you need something like reverse physics to understand clearly what the problems are and effectively with what the solution. So, how to participate and contribute to reverse physics? Well, first you need to share an interest in building a conceptual framework that treats physical theory as models of physical system, nothing else. So again, if you're interested in theories of everything, interpretations that equal quantum mechanics that have hidden variables or other things that are not measurable, these are not the things that we do. You can make passive contribution just by looking at what we're doing and, as I said, checking and make sure that everything makes sense to you. Or if you want to do an active contribution and you have sufficient background in some of the things, then I would say you can join our Discord server, and then we can have open discussions about this problem. So sorry for being rushed, but I had the problem at the beginning and I wanted to still leave time for questions. So now I have to open the Q&A. And I should also open the chat on YouTube.
Yeah, there are a few things already on YouTube.
Yeah, okay, let me go through there. Okay, so la, 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 la. Okay, so conditions are represented in different ways, but they represent the same thing, like different coordinate system mapping to some to the same absolute object. Yeah, that's basically what we want to say, because once you say that the conditions are equivalent to each other, they are basically telling you something that it's a more abstract conditions. And for example, in Hamiltonian mechanics, we saw that we have all these different conditions to recover Hamilton's equations that are all equivalent, and they are all equivalent to essentially the addition of two constraints, two assumptions, the deterministic and reversible evolution and the independence of degree of freedom. What is interesting is that these assumptions can go across theories. So the assumption of determinism and reversibility is something that we can take in classical mechanics, in quantum mechanics, possibly in field theory, and so on. So you should be able to take that assumption in any physical theory. So when we express it as a condition, we often express it in a condition over some base theory, right? And that's also something that is interesting, and conceptually we need to understand how to characterize these ideas in a way that it's a little bit more rigorous and less hand-wavy, if it can be done. Then on Zoom, could you clarify how we are to distinguish quantum context from boundary conditions? So the idea is that a quantum context is effectively a boundary condition. So as I was saying before, in the case of spin, you choose the magnetization of the electric field that you're using to prepare your electron. You have prepared a boundary condition, and then the electron will orient or anti-orient with that orientation. And it's when you change the orientation that you're forcing something to change, right? So you oriented your electron, now it goes and travels, and it's been in equilibrium, so it's staying there in its up state, and then you make it go through a different orientation, so you're changing the boundary condition that the electron sees, and then you're forcing the collapse into one of the two states. So if everything goes well, we want to be able to say that picking a quantum context means that, and the sort of the fact that you are then getting a probability distribution of these outcomes, it's literally you have a distribution over the equilibria, and mathematically you can do it by essentially projecting not the state themselves, but projecting the density operator. So whatever state you start, you go to a density operator that it's that commutes with the Hamiltonian that you set effectively, that basically. And that process, interestingly enough, is exactly an entropy increasing process. So the fact that you go from a pure state to a mixture of possible eigenstate, it's exactly you have increased the entropy. So you can literally see this as a type of equilibration process that follows thermodynamic ideas. So there was a question, what do you think of the relational reading of quantum mechanics? So relational quantum mechanics is a particular type of interpretation, and we are all that we want to say. We want to say it in a way that it's independent of interpretation. That's one of the goal of reverse physics, and we just want to show that the math works and I can say that the math has to be interpreted in that way because you're doing it implicitly anyway. Because on one side, if you assume that there are some, that there are some things that are processes, and you have a mathematical, that the projection follows mathematically these rules. And the fact that the outstates are left unchanged by the process, that's a notion of equilibrium. That's exactly what a definition of equilibrium is. And so we want to say that everything that you do on the physics side, it's exactly what's in the math side, that you can go back and forth. So at that point, which interpretation you pick doesn't really matter. You can say that these equilibria are relational, or you can say that they're ontic. I don't know. Whatever you want to say, you can say. For us, all of these things are models that we use in certain conditions. And what additional sort of setting you want to say about these models, you're free to say it. We don't. I particularly don't care. Okay, so going back, if there are no other questions, there were some questions from Julius about Hilbert spaces and all that. So one of the things that we saw at the beginning, then in Christine's talk, was that Hilbert spaces in the infinite dimensional case don't really work because they don't work well with infinity. And yes, there exist things called rigged Hilbert spaces to address some of these issues, but the problem is that they don't address is a rigged Hilbert space is a Hilbert space plus a smaller space, typically a Schwartz space, and then the dual space, which is where you have your delta Diracs and eigenstates that don't exist of momentum and stuff like that. And the problem with that is that you still have the things that is unphysical, right? The Hilbert space, what do they represent? Absolutely unclear. But now you have other two things. So you're not really making the problem simpler. You're making it more complicated because now you have to tell me what all these elements are. And what we are realizing is that there is actually we think at this point that there is a much simpler way to look at all of this. So one of the things that people don't realize when they're doing quantum mechanics with position is that since the position operator is not defined on all points, and since the momentum operator is not defined on all points either, the commutator can only be defined, let's say, on the intersection of those sets, right? And so when you write that the commutator between x and p is equal to I h bar, on the right side you have the identity. The identity is defined over all points. So technically, when you write even that equation, the commutational relationship, which is how we specify the quantum space that we're interested in, that equation is not correct in Hilbert spaces, because you're saying that something that has a domain of validity in a restricted set of points is equal to an operator that is defined everywhere, because the identity is defined everywhere. And if you take Schwartz spaces instead, position and momentum are defined for all states, which is good, and so that equation is valid. The problem that you have, though, is that Schwartz spaces are particular for distribution on position. And if we want to have something general, we might not have position and momentum, we have more of them, we have other operators. In quantum field theory, we have numbers of particles, we have lots of other operators. So it was not clear to me up until a few, I'd say a month ago, how do you generalize, what is the right condition? And we saw yesterday that Tobias was saying that the topology is experimental verifiability. So the topology tells you, and it's defined to be what things we can check experimentally, right? And continuity, the fact that the limits are well defined, is exactly what does not happen for position and momentum in the Hilbert space. Tobias showed the examples that you can have a sequence of states that converges to a ground state, but the expectation of some operator of some observable it goes to another value. And this is exactly the problem, that the operators are not continuous. And so if we say that the operators are continuous in the topology, we're literally saying that we identify quantum states, we verify quantum states through the observables. And that's exactly what we want to say. So if you put that requirement, if you basically say, oh, we have some vector space with an inner product which allows us to define our self-adjoint operators, and then we say we have a set of self-adjoint operators that are so important to us that characterize the space, and the commutator relationship between those operators are actually important to us, and those operator has to be continuous, and you're complete in the topology of those operators, then you get the right structure. And so in a sense, we understand probably now better these issues in quantum mechanics than in classical mechanics. And this is the fun part of doing reverse physics, is that once you see that all these theories are sort of sets of conditions that you can use from one to the other, some things are easier to see in classical mechanics, some things are easier to see in quantum mechanics, some things are easier to see in thermodynamics. And since you can now jump between one theory and the other, you can take the insights that you had from one theory and use it to fix the other theory and make everything more homogeneous. So this is the type of things that that I'm trying to work on, but I am distracted with a million things. So to Julius' questions, if rigor space is still problematic, what we want to do? We want to do something like this. We want to basically say we have one state space, which is a vector space, which has an inner product, which has self-adjoint operators that are observables, and you're complete in the topology of those observables. And that should probably be the right definition of the spaces that we need. And then you can define the dual, you can define your delta function of that, you can define your spectral theorem and so on. But that should be the core, that should be where the physics relies. Any other questions? Okay, since there are no other questions, I'll take a break and try to investigate what happened to my computer before to make sure that it doesn't happen again. And I'll see you everybody in 10 minutes. I see some questions appeared in the YouTube chat, so I'll try answering them. Let's see. Okay, so can I ask, are you interested in a subsection of the assumption of physics or all of them? What do I mean? Let me put it this. Consider that Newtonian mechanics produces equation that needs solving. Something happens and these equations are produced. Oh, it's not finished. So let me answer to Ahmed. In the field theory part, do you imagine it being like a discrete function of volume, meaning that the degree of freedom stays constant over some interval of volume, like the smallest volume containing only one degree of freedom? No. So in the field theory part, in a classical field theory where we're not trying to quantize the number of degrees of freedom, you should really have the volume should really be a continuous. So if you have in principle, if you have the same interval of possible conditions in each degree of freedom within the same volume, you should have, in some sense, the exponential of those conditions, right? Because if you have, three possibility over n degree of freedom, the number of total cases would be 3 to the n. And so if we have some sort of set of configurations within a field at each point, then the total number of configurations should be the number of configuration per degree of freedom to, the number, the volume of space, right? So that's kind of what I would expect this computation to work, and the volume could could shrink and become small. And then, of course, you see the problem. That if this volume becomes small and small and small, at some point it becomes close to zero, and then you have the exponentiation of zero, and so you have one, so you have sort of weird things like that. And but I don't know exactly how that works, and if it's the right idea. I don't know if it's the right idea, and I wouldn't know how to make an integral of something that has an exponent. I saw that there are things that I call geometric interval that allows you to take this and transform it into something else, but it's all stuff that I don't know how to do. And then going back to CanValid, can I ask, are you interested in a subsection of the assumption of physics? Grow them. Consider that Newtonian mechanics produces equations that need solving. Something happens, and these equations are produced, and then the solution are found and translated into prediction. But you can imagine that there are correct and incorrect ways to formulate the equation, and there are type checks that exist to prune the equation that becomes acceptable, that involve the behavior open and closed system and produce constraints. Yeah, that's basically it, right? We want to know what are all those conditions. So once you write, so right now we basically start saying, oh, we have these equations, right? But maybe when you write the equations of Newtonian mechanics, you have some implicit assumptions that that tell you that some other condition that you could write, or some of the equation that you might be tempted to write, are not actually consistent with the assumption that give you the equation themselves. I don't think this is going to exactly happen in Newton mechanics, except for those cases where okay, let's give you this might be a good example. So let's say you write equation of your forces and your Newtonian mechanics, and now you have equations that are not differentiable. Now, if the equations are not differentiable, if you have a probability distribution and you try to evolve it with Hamiltonian mechanics, your probability density is not going to be mapped very well, right? So if you want your probability density to be mapped well, that's an extra condition that you're putting on just the pure Newton's equation. And then you should ask whether is that an independent condition, or it's something that, in some sense, it's about things that you need to have anyway, right? And I don't care to know, in some sense, what are the correct conditions, right? I only care to make all these conditions explicit and all the assumptions explicit, so that we can reason on them and see whether those things make sense for the physics or not. Like, this is all what I want to do. And then a follow-up from before, I think it's not about quantization in the regular way, but making maybe classical fields inherently discrete over continuous space-time, and maybe a new principle like a maximum degree of freedom for each value. Uh, Again, it's not about being discrete. If you remember that slide that I had, like discrete means that you're saying that finite things become infinite. So that's not what you want. So if we are sort of quantizing the number of degree of freedom, you really want a volume that you shrink, and when you shrink it, you keep decreasing the volume continuously, but then when you get to a single point, you get to a 1, you don't get to a 0. And I think I have to start the new section, otherwise I'm going to be late for other reasons. So let me start the new section on the open problem of physical mathematics, and we can go back to everything that we want after we went through this. Okay, so we saw reverse physics, and now we're going to talk about open problems in physical mathematics. One of the things that I didn't mention before, and I should have said before, I thought I put this in the other slide, but I have started to create a searchable section of open problems and conjecture. That it's so you can go to a website on the problems, put in a keywords, and things will appear. And when you click, you are going to be redirected to a section with an open problem in the book. So what I want to do is slowly sort of specify all these open problems within the book so that we have this infrastructure that whenever something gets updated in the book, all the indices in the website gets updated and people can go and search these things. So even if you can't help solve a specific problem, but you help me clarify and make sure that all these open problems are in the book and they are complete, that's already a tremendous help. So yeah, I appreciate a lot more people that help me with this sort of tasks of getting everything to work at an infrastructure level. And like I really appreciate it. Like you think that those things might be less important than the actual research. I actually think that in some sense are more important. So anyway, overview of where we are. There are essentially 3 layers that I originally thought we need, and I still kind of think that we needed, though the thing in the middle. I'm starting to not really understanding how exactly should be shaped. But we have a layer that basically imposes experimental verifiability and that recovers topologies in sigma algebra. And this I would consider done, though probably there are things that could be done better. That might be connection to some things that people do in category theory that may be interesting, people might work. Anyway, so the point is that the core connections are done. And I tend to try to work on the core connections to make sure that at least we have sort of the skeleton of the whole thing done, and then other people can help me fill in the pieces, but I feel that I have to work on these harder problems. The section above, it's about information granularity, so something that we should need to define in general, a physical dimension, unit, and other ideas. And I touched these things at least 4 years ago last time, and even just cleaning up what we have found and what doesn't work and what works, that probably might be useful. And then we have sort of the theory of states and processes in a general sense. And this is where we did we started this work on ensemble spaces. And this actually is going very well, and there are a lot of open problems. In fact, the most clear open problems are starting to be in this section. It's fairly mathematically sophisticated, so there are things that we need there that are interesting to go and look for. Okay, so let's start with information and granularity. The goal here is to establish a mathematically precise notion of units, physical dimension, and the required minimal assumption. The general idea is that we have a partial order on all statements where physical dimension define a classic of statements that are comparable to each other, and these classes are isomorphic to the real number. So the idea is, well, we'll see it more in detail later. Some insights have gained, but I don't think we have a general solution, and there are notes in this GitHub repository that, again, it would be nice to clean up and add it as an open section, open problem section in the book. And again, this is something that somebody can definitely help me do this. And this has been on the back border because we have been working on ensemble spaces yes, and we can't do everything. So what we need to do, as I said, would be to clean up what we already have, which would be nice, and then finding necessary and sufficient conditions to recover the appropriate sigma algebras. This is not clear how to do it, and then understand whether there are problems regarding the non-additive measure that we find in ensembles, because we were assuming additivity, and so that there is some sort of mismatch now between the old stuff and the new stuff. So the basic insight, though, is absolutely valid, is that with the logical relationship, we can only compare things that are fully contained in each other. So we can say that the position of the object is between 0 and 1 meter is a narrower statement than the position of the object is between 0 and 1 kilometers, because this is fully contained in this. So this is clearly bigger than this. But we can, if there is no, if one is not contained in the other, maybe there's just some overlap, and then we don't know which one is bigger. Topologically, you don't know which one is bigger. Same thing if the Faraday is aligned of 1, that's definitely a narrower statement that the Faraday die landed on 1 or 2, but again, if there is mismatch, you can do it. And this granularity relationship, something is it's sort of is finer, it's a finer statement than other, then this is actually equivalent to notions of geometry and probability of information. Because if I say that the position of the object is between 0 and 1 meter, it's a finer statement than the position of the object is between 2 and 3 kilometers. This is exactly saying that this distance is smaller than the other distance. So notion of fineness of your statement is equivalent to notion of geometry. Same thing that if I say the Faraday landed on 1 is a finer statement than the Faraday landed on 3 and 4, I'm basically saying that this one is less likely, that the probability is less, and that the first bit is 0 and the second bit is 1 gives me more information than just say that the first bit is 0. So there is this insight that measure theory, geometry, probability theory, and information theory all quantify the level of granularity of different statements, and this is again the equivalence between geometric structure, information structure, and probability. Like this we said it before, there is this common theme, and so it would be nice to be able to characterize this in a way that it's mathematically precise. So the idea is, since we need to be able to compare all the statements at different level, a single measure is not enough. So, for example, let's say that I have a statement A that tells me that the position of the system is exactly this point. I have a statement B that tells me that the state of the system is one of these 2 points. I have a statement C that it tells me that I'm exactly this value of momentum, but this value of position, and same in reverse for D. Or the statement E tells me that we are in this set of possible state. Then A is finer than B, and it's finer than C, and it's finer than E. But it is not true that C and D are comparable to each other, because a range of position cannot be compared to a range of momentum. So it's a partial order because we can compare, we can try to compare any 2 statements, but some statements are just not comparable. And the idea should be that the class of things that are comparable in some sense it tells us which unit you have. because once a unit is chosen, then you should be able to have a measure that quantifies the granularity of another statement with respect to the unit that we've chosen. So if we chose A as a unit, then B would have twice as many points, so we would say, it's measure 2. If we took B as a unit, then A should have measure 1/2, right? So we should be able to sort of identify units as sets of statements that are comparable to each other in a finite way. Like you can say, if I can say that this statement is twice as big as this other statement, then it means that in a unit that I pick, the value is going to be twice as big. So we had some ideas, we had some definitions, and they actually, these things actually work well, allows us to sort of prove a lot of things. So these basic notions are probably good. What we do not know how to do is, if we pick a unit, to essentially define this measure that tells you which statements are comparable and which value do you give. So the problems are, given a U, when is this measure unique? No idea. And what is the algebra all comparable statements, and whether this algebra is unique. We know about what we want is that once you pick a unit, the measure for that unit has to be 1, and the measure has to be monotonic with respect to this granularity ordering. So if S1 is finer than S2, then the measure given to S1 has to be smaller than the measure, smaller or equal to the measure of X2. And we want to say that if two statements are incompatible, then we have an additive measure. And so the question is, are there restrictions on which statement can be taken as units or on the initial state such that this can be done? And are there compatibility requirements within the topology, that you need some limits to exist and so on? This is a completely open problem. I don't quite know how to address it. I think if somebody is interested in order theory and sort of the nuts and bolts of math, this is a really interesting problem, but it's a complicated problem. So that's why I left it there. I can make progress in other in other areas, and so that's what we've been doing. So there is this notion of the differentiability that we also want to recover from definitions that are physically clear. The convergent definition of tangent spaces and differential in differential geometry do not work well for physics, mainly because of units. And interesting enough, the definition of variation calculus, which are the one that one uses in infinite dimension, actually seems to be closer to what we need. And so we have an initial prototype that does these things, and I'll go through some of these ideas. And we talked a little bit, we think we made a live on some of these ideas as well. And again, if somebody wants to work on this and sort of clean up the prototype and actually make it work in the way that it should, then it would be good. So the idea would be that once that it's done, we should be able to interpret the use of differential geometry in physics. Based on this, we work the definition. So the notion of Lie derivative and all these other things that one have in differential geometry have a much more operational understanding on all this. And there might be work that has already been done in other books that we could buy. We might be able to take advantage of. It's an open problem for me. I don't even know what is there to be useful. And so this is essentially the problem, has been that the mathematicians have developed in terms of differentiable structure and differential geometry, developed definitions, algebraic definitions that are useful for them, but they're not really so useful for physics. So we saw that, I don't remember who said it, but in one of these lectures we saw that in differential geometry one defines vectors as a derivation, and you have a vector basis that it's a derivation in different coordinates. but derivation of different coordinates means that you can't sum them if you're using different units, so this does not quite work. Plus, velocity is not a derivation, right? It's a ratio between space and time with particular physical dimensions. So that's not what exactly is. The other thing is that hidden in the differentiable structure there is a notion of the differential, which is the one that uses essentially the Frechet derivative. But then on top of that, you define a different notion of differential, and I don't like that. I'd like to have one notion of differential so that when I write dx, it's the same thing for different in different cases. Actually, this is always the same thing. So if you have never seen differentials or one vectors treated in differential geometry, they're basically defined as maps between vectors to real numbers. So a differential literally takes a derivation and gives you an element which is the component of the derivation along that. And a momentum is a covector, so it should be one of these things, but it's not one of these things. A momentum is just a set of numbers that we use to identify a state, so which with particular rules under coordinate changes. So this is not exactly what we need. And really what we'd like to have is this idea of infinitesimal objects that are limits of some finite objects. Not that we first define the differential of these infinitesimal objects and then we integrate them, because really the physics works the other way around. We only work with finite things and the infinitesimal is the limit that may or may not exist. So the finite things are the things that we measure. The infinitesimal things are the limits we don't measure, are the parts of our theoretical apparatus, and their abstractions. So I've been thinking about what is differentiability in physics and how can I define, and there is a sense that we want to say that infinitesimal reducibility is what gives us differentiability. It's the idea that we can take something finite and see it as a sum of infinitesimally many pieces. And what we want to say, for example, if we have a curve, and you can imagine to have 2 points on the curve, this gives us a distance, a vector in the coordinates. And you can imagine now that these 2 points converge at one point, so we have a sequence of vectors. And we want to say that a differential is basically this sequence of vectors, the things that we're getting smaller and smaller and smaller, that at some point converge in the limit to a tangent, to converge to something. So if you had a sequence of vectors that kept rotating, even if the rotation goes to zero in a spiral, that's not a differential, because you're not converging to zero, you're not going to the infinitesimal small along a particular direction. And so we want to have this idea of differential as things that become small, sequences that become small along a particular direction, so that we can have a structure like this. So we have space, we have a trajectory, which is a function between time and space. And let's say that we have temperature as a field, which is a value given an element of space. So we have these three quantities, and we have a map between them. And then we want to say that the differential are these infinitesimal changes. So if we have an infinitesimal change dx, through this map, we'll get an infinitesimal change dx. So an infinitesimal change in time will give us an infinitesimal change in space. And the derivative, the velocity, is the map that goes from the infinitesimal change in time to the infinitesimal change in space. And then we can do it also for the temperature. If we have an infinitesimal change in space, we'll get an infinitesimal change in temperature. And the gradient is exactly the infinitesimal change, the map that goes from an infinitesimal change in space to an infinitesimal change in temperature. And these maps, these x and t, are differentiable if this map exist. If we, in the limit of making things small, we're mapping small changes to small changes. And note that this is a one-dimensional manifold, this is an n-dimensional manifold, this is a one-dimensional manifold. So this idea works both for maps that go from one to many, which means that this is going to be a vector, and for maps that goes from many to one, and this is going to be a covector. So the whole idea of what is a vector, is a covector, what is a tensor, it's basically built in the dimensionality of these two elements, right? If this is n and this is m, we are going to have a mixed tensor with n indices down, because this appears down, and m indices up. And this essentially gives you a very clear understanding of how units and how these maps work when you're doing relativity. You have all your tensor with the indices. This is exactly what you're doing. You have changes in direction that gives you changing in other direction. And so now these things that we typically think of bases, these are not bases, right? These are maps from the particular d-axis to particular dp, right? So dp is going to be the displacement on the manifold, and this is unit free. These dxi's are displacements in the coordinates, so they have units, and these are maps that tells you for these displacement in these units, I will get a displacement unit-free element in the space. And so this should allow us to define all these things in a way that it's nice, and in a way that makes sense for the units, and hopefully that we can also generalize to infinite dimensional spaces, because all these ideas of differential essentially just use the vector space structure, and they don't use the fact that you have something that is finite dimensional. So mathematically, this is kind of what we have. We have an idea of a convergence envelope, which is a sequence of non-zero elements of R that goes to zero. So it tells you how we're becoming small. And then a differential is a sequence of vectors such that when we're becoming small, we are going to have a tangent. The changes goes through a particular direction. And this only requires a topological vector space structure, and it's closer to what one does in a differential analysis with a variation. It's just that this variation may not come exactly from a single direction. It's something that tends to a single direction, so that we can do coordinate transformation, which are the typical thing that one does not do in variation calculus. So now if you have a differential, what you can show that you can always write it as essentially the product of the convergence envelope. The tangent vector is something that goes to zero, and you can always take one of these constant and either apply it to the tangent vector, or apply it by rescaling the convergence envelope, and this is sort of a differential. So this is a differential with convergence envelope AI and with tangent vector kt, and the k can be moved from one to the other, which then allows you to show that differentials with the same convergence envelope form a vector space, and this is where you get the vector space structure. So you have a vector space, you fix a particular AI, now you have a space of differential, and again, this don't know that you are in finite dimension. You can use this however you want. Then you have a notion of a map, and you can essentially map these differential through the map by doing a difference, which is kind of what we would expect. And the map is differentiable if when you're taking a differential with a convergence envelope AI, what you get through the map is another differential on the new space with the same convergence envelope, and the derivative is a function and only a function of the original tangent space. So you're basically saying, I'm going to zero in, I'm getting my changes both small in both spaces, and I can identify that if I arrive to my zero in this direction, I will be arriving to my zero in this other direction. And so differentiable maps are those maps that map differential to differential with the same convergence envelope. What is cool about this is that the derivative can be shown to be linear. Like in Fréchet derivative and antiderivative, either the derivative is not automatically linear or you have to force it to be linear. And what is nice is that this definition already tells you that the map has to be linear. And it generalizes the Fréchet derivative, which you can recover, and you also can recover other standard notion of derivatives. So I think this is promising as a way to do it, and you can recover the chain rule if you have U, V, and W with a map F and G, and you have the composite. Then the chain rule is simply the concatenation of the two. Like it's the composite. It's just function composition. And the proof, again, it's simple. It's like not even a page, which again, you know that you have good definition when the proofs are general and they're short. It means that you have the right starting point. Okay, so this recovers the standard definition in the standard cases when you're mapping R to R or when you're mapped to two normed spaces. And so this is kind of like what I was saying before. You have a space X and a space Y. You have local coordinates for X and you have local coordinates for Y. You have a map from X to Y. You have the map for the coordinates. And now you can have all the maps that allow you to express the function from coordinate to coordinate, from differentials on the units to the other differential on the other unit valued quantities. And so you can write all these things, and all these things sort of work well. Of course, we would have to go through all the definition, make sure that everything works well. There was a question of why do we have local convexity, and I think I understand now why local convexity is needed, but right now it's not being discussed. As I said, it's just basically a prototype. And the thing that we want to do is also to generalize this idea of differential forms so that we have a better sense of how they work. And the notion here is simply that if we have a temperature, the temperature is a function of a point. Work is a function of a path, magnetic flux is a function of a surface, and the mass is a function of the volume. And the one form essentially become the infinitesimal elements that are basically derivatives. So a force is something that, given an infinitesimal path, gives you the infinitesimal work that then you sum up. If you have the magnetic field is something that, given an infinitesimal area, gives you the infinitesimal contribution for the flux, which you now integrate. And a mass density is something that, given an infinitesimal volume, gives you the infinitesimal contribution of the mass, and you go and integrate it. So what I'd like to do, which I still don't know exactly how to do, is to be able to define these forms as effectively something like Radon-Nikodym derivatives that, so in measure theory, when it works for volumes, like these two would be measures on the volumes, and the Radon-Nikodym derivative is really the ratio between those two measures. I'd like to be able to see one forms in this way, so it's kind of like more measure theoretic than differential geometric, but they're the same thing. They should be the same thing, and should give us more of a physical intuition, because these, like the finite quantities on surfaces, on finite regions, are the ones that we measure. Like that's where, you know, the difference between a magnetic field and a force come from, is that the magnetic field is a function of a surface, because when we go and measure, we don't measure the magnetic field, we measure the flux, and the flux is measured on a surface. And I think this would also be required to really understand Maxwell's equation well, because when you go, when you're taking the curl or the divergence, you are thinking of the electric and the magnetic field as function of surfaces or lines. So technically they are telling you something different operationally. It's a different operation, and those are the things that I still don't quite understand, and they needs to be clarified. Another side effect of writing this way, which I do not think I have time to go through all of this in detail. Let me check how many slides I have. No, okay, I have to be quick. I'm already behind. It gives you a better intuition of the exterior derivative and things like this. So now the exterior derivative in this context, it's not the definition. You show that you have this notion of boundary functionals, and this corresponds to the exterior derivative. So in differential geometry, you have the Stokes theorem. That is the theorem that you prove once you define the exterior derivative. We basically define things through the Stokes theorem, and then we find that the exterior derivative is the operator on these infinitesimal forms. So we have relationship on the finite, and then we show that the infinitesimal elements are linked through the exterior derivative, which again I think it's the better physical way to understand this. Yes, then if I did write, there is a video on my channel that shows how this can give you an intuitive understanding of what the vector potential is, and I think this is exactly the type of things that one needs to have to get these definitions and intuition much better. Okay, so this is a whole kind of worm. Another kind of worm is the idea of topological convex spaces. We need to develop a theory of topological convex spaces because, as we saw yesterday, ensembles form a convex space that have a topology, and we need to understand what's the theory behind this. And there is little work on these things. There is a lot of work on topological vector spaces, which means you can make arbitrary linear combinations, but we right now cannot tell that ensembles cannot make arbitrary linear combination, and they're going to be smaller, they're not going to be vector spaces, and so we need to understand how this works. So ideally there is space to really create a self-contained mathematical theory that is even disconnected from what we do. We need to understand when topological convex spaces embed continuously in topological vector spaces, and understand which result from topological vector spaces can be generalized to topological convex spaces. So these are basically, in a nutshell, what we need. As we saw before, we have an axiom of ensemble that gives us a second countable topology. We have an axiom of mixture that tells you that you must be able to make convex combination. So these are necessary. And the question is how do convexity and topology interact. So a lot of progress in the last 6 months. Many conjecture were proven or disproven, but there is still a lot of work that still needs to be done. And just to give you a sense, some of this progress has been made by a first-year undergrad that worked with me as a Europe student here in the University of Michigan, and is still working with me over the summer. And we are, doing things together. So it's not, it's technical. You need to get used to some concept, but it's not that you need 3 years of requirements to be able to understand what it is that we're doing, which is kind of interesting. Okay, so once we have the convex combination in 2, we can extend to the finite convex combination, and we can also extend of convex closure to include infinite convex combination. So it's the topology that tells us which infinite convex combination work or not. The question is whether we can define a notion of convex interval. And so instead of using points, right, and summing them, we could have a probability measure, right, and we make the integral according to that probability measure, and we find the elements. So this is also called barycenter algebra in some context. And so the question is whether we can define a notion of convex integral, and whether the unicity of that integral is equivalent to the existence of a unique barycenter, and therefore a locally convex topology. This is something that would be interesting to understand, and this is an open problem in a draft that you can go and look and see what you think. We can prove that the convex space is concatenative, meaning that it embeds in a vector space, but we do not know whether the embedding is continuous. So is the topology the same? Is the topology compatible to the one of a topological vector space or not? It's unclear. So the question is, when is the embedding continuous? For example, can a T1 second countable concatenative topological space embed non-continuously in a topological vector space? I think the answer is yes, because I think I found a counterexample, though I am not 100% sure. So again, if other people that double check what I say would be helpful. We think we can, that the finite dimensional topological vector space with the same dimensions are isomorphics, and we do think that something similarly holds for topological convex spaces. In fact, we are able to show that if the topological convex space is Hausdorff, the embedding has to be continuous. This is something that I'm working with the students right now. We think we have a strategy, we think we have a proof, we're doing the due diligence to see if the proof actually works. Now, one of the problems between the difference between topological convex spaces and topological vector spaces is that the topological convex spaces, especially the one that we're interested in, have edges. And so the open sets around the edge will look fairly different than the open sets within the bud. So the question is this, whether this is the only problem. So for example, do two internal points always have two neighbors that are isomorphic? Again, I don't think so. We should, so for all this conjecture, you say, oh yes, this is true, and then you find that they're false, so that, that's how you proceed. And then the question is whether any second countable T1 topological vector space is automatically metrizable. So no, this is not a question. This is a statement of fact. In topological vector spaces, any second countable T1 space is automatically metrizable. The question is, does something hold for topological convex space in the same way? This I really have no idea. This would be a nice result to be able to prove this or not. So these are the type of things that are in physical mathematics, and as you see, they're really like abstract math work. It's really nuts and bolts of the math that we need to work on, which is exactly what we want. If we want to have mathematical structure derived from physical principle, then we need to know exactly what those nuts and bolts of the math are, where they come from, and how we can get to them. So another area, and again, I'm just giving you sort of a sense of what the open problems are. If you want to drill down in the details, we can schedule then other discussions. We saw that there is this notion of equivalence between geometric structures and definition of entropy, and so that's exactly what we want to be able to do it, right? We want to be able to do that formally and see that all of this works, and we have some pieces as we saw yesterday, but there are a lot of other pieces that needs to be done. So we need to understand the role of entropy in defining limits and therefore the topology of the ensemble space. This actually, we started having some better idea in the last couple of months. And we need to understand what properties can be generalized from classical and quantum spaces, and how can everything work in field theory. Because again, I do not know how to put an entropy on field theories. So once we have a set of ensembles and once we have an entropy well defined, we can ask how much does the entropy increase during a mixture. So if we have A and B, and we make an equal mixture of A and B, how much is the entropy higher than just the average of the entropies. And this is actually a quantity that is non-negative. It's zero only if the two things are the same. It's bounded by the unit, and it is the unit only if the two things are mutually exclusive, if they're orthogonal, and it's a symmetric quantity. It's a pseudo-distance that it's defined from the entropy. It's a pseudo-distance because it does not satisfy the triangle inequality, but recovers the Jensen-Shannon divergence both in classical mechanics and in quantum mechanics. Now, in classical and quantum mechanics, this quantity is the square of a distance function. And the question is this true in general? Probably not. It is true. I think it's going to be true for orthogonally decomposable spaces. And the question is, are we missing some axioms that would make this the square of a distance function that are justifiable from the physics? I have no idea, but maybe there are. And if that would be true, it would mean that all ensemble spaces are in some sense they have a distance, although they might not generate the topology, but we would have a distance. One of the things that I was able to prove last year is that if you have A and B and make a mixture of A and B, right, as you go closer to A, the MS goes to zero, it decreases. What happens 2 months ago is that one of our students actually proved a better bound. So instead of just saying that MS of AB is greater or equal between, of the MS between A and a mixture of A and B, we can actually show a triangle-like inequality, so that essentially the distance between A and B is greater or equal to the distance between A and a point between them and B and that same point. So that is kind of a nice result. And again, it shows that there is possibility for students to make contributions. Another question is whether the mixing entropy fully specifies the criteria of convergence and therefore the topology. If I have a sequence that goes the convergence to another point, and a sequence of ensemble that converges to an ensemble, then the mixing distance will go to zero. Is the reverse true? It seems that in the finite dimensional case it is true, but not in the infinite dimensional case. And in fact, it seems to be that the convergence of this distance does not even guarantee the convergence of S. And this is kind of interesting because the topology generated by this function is the same topology that one uses in probability spaces. And this is basically telling me that when we have a space of probability distribution, and we put an entropy on that space of probability distribution, the entropy is not a continuous function in that topology, which again tells me, like we were saying in quantum spaces, we don't have the correct topology. So again, this is one of these issues that, you know, looking at the details tells you and uncovers problems that probably need to fix. And from this pseudo-distance, you can define open balls, more or less like you do typically in topology, and you are asking whether this subtopology is, what is this subtopology, whether it's interesting and so on. So there are, again, this connection between topology, topological convex spaces, and entropy that it's kind of interesting and need to be uncovered. So one of the other open problem that is interesting in the classical case, this is a discrete classical case with 3 states. This is a point, and these are these open balls of mixing entropy. So you get a cutoff, and you're taking all the states that are less than 0.04 mixing distance away, so you get these balls, and you note that these are they're convex sets, and it's the same, they're convex in quantum mechanics. Now, it seems that from the theorems that we do not have enough constraint to make sure that these entropic balls are always convex. So for example, this is another entropy that I could put on the space that would still satisfy the axioms, but it's definitely not convex sets, that the open balls are not convex sets. And so the question is, do they have to be convex, or it doesn't make sense physically? And again, this is exactly questions that are in between math and physics, try to understand whether physical conditions, mathematical conditions are physical or not. As we saw yesterday, the entropy imposes a metric on the ensemble space, and now we need to make sure that this works properly in finite dimensional cases. We found some problems that are also there in entropic geometry anywhere, so I'm not too concerned. But anyway, these are kind of the work that would need to be done in entropic geometry if somebody is interested. And then there are even more ill-defined problems, because a lot of the time finding the problem definition is the actual problem. So how does the geometry of the space of ensembles relate to the geometry of the space of states? How do you do this in general is not clear. Given that the mixing distance is between 0 and 1, and 0 when they're the same, and 1 only when they're orthogonal, can this be turned into an inner product? Is there a general way to do it? Who knows? And can we generalize some results from entropic geometry, like co-level bounds and other things, to ensemble spaces so that you have the same statement that is valid for both classical mechanics, quantum mechanics, and possibly other unknown theories? So these are open questions in that area. Another area of research has been how to generalize measure theory such that we have a generalization that works for both classical and quantum mechanics. In classical mechanics, we have a notion of a probability space where you have a sample space, a sigma algebra of the event, and a probability measure. The sample space are basically the possible things that can happen. The events are the tests, and the probability measure is something that associates 0 or 1 to the outcome of a test. Then we also have a state count that, given a set of states, we know how many states are there. And a probability distribution is the derivative between the probability measure and the count of states. And this exists precisely because the probability is absolutely continuous with respect to the count of states, meaning that if you have a region with 0 states, you better have 0 probability. You can't assign non-zero probability to a set that has no states. So these are standard definition. And then you have a definition of random variable, that it's a map that assigns a value to every possible outcome, and then you take the expectation as being the integral of that function with respect to the probability measure or respect to the probability density. So this is how things work in classical mechanics. The problem is that in ensemble spaces, in general, the probability that you use, the coefficient that you use for making a mixture are not exactly the probability that you get out. They are the same if and only if the mixture, the elements that you're putting in are orthogonal to each other. They're mutually exclusive. And this is exactly the notion of a quantum context generalized in the notion of an ensemble space. You get a probability of outcome only if the outcomes are mutually exclusive. They represent things that are different from each other. And so the idea is that we want to be able to have a standard generic measure theoretic tools to describe these mixtures and preparation, and we need to understand how to do it. And we probably not gonna be able to show everything, but generally the idea is that as Tobias showed yesterday, we have this idea of a state capacity. So given a set, we want to be able to know how many states can be encoded in this distribution, and there is a sense that the exponential of the entropy is the only way to quantify that, and this is actually a new development of the last month. We were able to show that this is a unique functional that has a specific property, and that state capacity is is like a measure in the sense that it's a non-negative monotone, and it's additive over orthogonal sets. So in some sense this generalizes the Liouville measure as the Cantor states, and it also works for quantum mechanics, but the problem is that it's not additive over non-orthogonal sets. So in general, in quantum mechanics, this would be a non-additive measure. So the idea is we need non-additive measure theory to be able to generalize these ideas. For the notion of probability, we are basically asking, instead of probability of outcome, mixture coefficient, the highest mixture coefficient that we can use from a set of states to get the original state. So basically you have an ensemble E, a set of ensemble, and you're asking how much of E can be generated, can be done by mixing the elements of set A. You are going to get a maximum P, which is going to be what we call the fraction capacity. And the fraction capacity is again a set function. Then it's non-negative and unit banded. It's monotone. It's continuous from below and above, and it's subadditive. And in some sense, it recovers additivity in some kind of way through orthogonal sets, but it's a little bit more complicated. But it is basically a probability measure, except that it's subadditive instead of being additive. We also have a notion of statistical quantities that are basically just quantities for which the mixture of the quantity is the quantity over the mixture is just the average of the quantity itself. And what we'd like to, and we know that in the classical case, these become integrals of our random variables. In the quantum case, these become traces of some Hermitian operator. It's also true that this is not all affine quantities are come from this. There are some that don't come from this, and an open problem is understanding how to distinguish them. But suppose that we are able to distinguish them, what we want to be able to know is essentially use the state capacity as a Liouville measure, the fraction capacity as a probability measure, and we want to be able to know that there is a probability density, which is going to be some type of derivative between these two things, such that we can go and reintegrate this and have sort of the same pattern that we would have in classical measure theory, in classical probability theory, but instead of with additive measure, we would have some non-additive equivalent. And this is a completely open problem because there are already non-additive measure theoretic tools, but they don't have the property that we want. So this generally seems to need new math being developed, and we're trying to find collaborators here. We are actually going to have a workshop in the next 2 weeks on this problem specific, because this is a really hard problem. I thought that we could just get off-the-shelf solutions, but it didn't seem to be possible. Very quickly, last thing is that we need to find a single structure that generalizes the classical Poisson brackets and the quantum commutators that works on the generalized ensemble space. And basically saying that the difference between classical and quantum mechanics is where the observable commute is non-centrifugal, because you are comparing things that are completely different from each other. What you have to compare between classical mechanics and quantum mechanics is the Poisson bracket structure with the commutator structure, and they are the same. You have the same relationship. So you need to understand what is that relationship describing in terms of ensemble, such that we can generalize and put it in ensemble space. So the algebraic structure are the same, but they're implemented differently on the different space, and this is likely is going to require a different axiom, but parts of these elements are actually should be already embedded in the axiom of entropy. So it's again one of those questions where we have to understand which part we already have with the current axiom and which actually is the new part that is independent from the other axiom. And so we need to understand how to define this common structure and then create a theory of processes and transformation that is common on all ensemble spaces and show that this reduces to the one for classical and quantum mechanics in the appropriate conditions. So that we recover the Poisson brackets in classical mechanics, we recover the commutators on vector spaces in quantum mechanics, but if we are doing quantum mechanics on phase space, for example, we would recover the Moyal brackets, which is another way to represent commutators. So this is the structure that is common. Suppose that you have a Hamiltonian that it's the generator of an infinitesimal transformation where t is parameter of the generator transformation. In classical mechanics, you write that the derivative of f of a quantity with respect to t is equal to the Poisson bracket between f and h. In quantum mechanics, you write that the derivative of the observable with respect to t is the commutator between O and h divided by h bar. Both of these are skew-symmetric brackets that tells you how the variable, how the observable changed during the transformation. It's exactly the same. This is exactly the things that we need to generalize such that we have it in the ensemble space without even knowing whether we are doing classical mechanics or quantum mechanics. So in the ensemble space, we have statistical quantities. So we have the idea that our f's could be, in classical mechanics, the integral of the probability distribution or the trace of a density operator in quantum mechanics. And we can define now a bracket that gets implemented through the Poisson bracket in classical mechanics or the commutator in quantum mechanics. What you can show is that this is a Lie algebra, because it inherits the property from the fact that the Poisson bracket is a linear algebra, the commutator is an Lie algebra. So the idea would be to sort of invert the thing, right? Say in abstract that we have a Lie algebra and that that this Lie algebra will have the property, and then we can prove that this Lie algebra is exactly those two Lie algebras in that space. This is the part that I don't know doing. So the Poisson bracket, though, it's a little bit more than a Lie algebra. So in both cases, these operations act as a derivation, right? And so the question is whether this thing that we have defined on top of these also acts as a derivation, and also I can define it as a product. The Poisson bracket, the fact that these two things are Poisson bracket in a more general sense, means that the active derivation of the associated product, but I don't know what the product is, because it's definitely not the product of statistical variable, because the expectation of the product is not the product of the expectation, so this does not work. And so how are we going to define this product? Can it be defined in terms of generator of composite transformation? Can we use non-commutativity of the variable based on the non-commutativity of composite transformation? So all of these things needs to be understood. How can we properly define this structure more in general such that we get the right condition, and can it be? So what new axiom is needed at all is basically what we are going to look. So these are both deterministic and reversible transformation because they leave the entropy unchanged. So the canonical transformation of Hamiltonian evolution is deterministic and reversible, and so is the same the Schrödinger equation unitary evolution. So there is a compatibility condition between these brackets and the notion of entropy. And also this structure guarantees us that there are always tensionary ensemble under each deterministic and reversible transformation. So any ensemble, both in classical and quantum mechanics, you can find a Hamiltonian such that the ensemble not change. There are fixed points on that transformation. So the question is, can we turn it around? We already assumed the ensemble must be equilibria to have an entropy well defined. Is assuming that every ensemble is a stationary state of some time evolution enough to say, oh, then we must have this structure? I have no idea. I don't know what this structure is representing physically, and therefore we need to do the work. Okay? So, wrapping it up, so we strongly believe that it is possible to create a solid mathematical framework for all of physics that starts from physical requirements. that mathematicians can be guaranteed those axioms are satisfied, and we have a clear idea of what we are talking about. And to do so, we need to construct all the needed mathematics from ground up, because there is no chance that mathematician, by coincidence, gave us exactly the right starting points that we need. It's not going to work. Sometimes this means reorganizing core mathematical ideas in different ways that may seem confusing and pointless to a mathematician. And on the other hand, there is new and interesting math that needs to be developed, because we are generally looking at new problems that mathematicians have not looked at. And this is, again, a huge undertaking that spans multiple different branches of physics, math, information theory, and also some philosophical idea. And so we need a coordinated effort from a group of very heterogeneous experts that can allow us to do this. So again, there is space for everybody to sort of try to get a piece. And the important things to me is that all those pieces need to fit. So the idea that a mathematician goes away for 6 months and comes with something, or anybody comes with something after 6 months, there's going to be very little chance that the pieces are going to fit with everything else if there wasn't some good understanding and agreement in between. It's basically more of an engineering project than a research project, because you need to make all these pieces fit well together. Otherwise, there is no point. Okay, so I did the hour. I don't think there is anything else here. This is same as before for physical mathematics. If you want to become a consultant, it's just, oh, I'm just a mathematician. From time to time, I'm willing to have a chat on these details. That would be great. And for the case contribution, we should probably talk about, and as I said, we can have live discussion or other discussions. And we can open it up to questions. Okay, so okay, I don't know who started the question first, so I'll start with the Zoom ones, and then I'll go back to the YouTube one. So what do you mean by saying that the differentials are manifold? The differentials are not manifolds. They are they form a vector space. I guess infinite dimensional they would be manifold. Maybe I should get the slide back. That's so the differentials are really the space of sequences that converge to zero. Let's see if I can find it. Yeah, so a differential is a sequence of vectors that basically goes to zero, because this limit has to be well defined, and therefore this is gonna converge to zero to be able to work. And for each quantity, you're going to have a space of differential. And the space of differential is going to be a vector space no matter what. If you are a finite dimension, then kind of finite dimensional vector spaces, finite dimensional real vector spaces are manifold, so kind of tautologically you have them. But in infinite dimension, they're definitely not going to be manifold, and it's probably going to be the interesting case, or uninteresting case. Okay, then on the YouTube chat, let's see. What about physical theory of temperature and energy due to vague understanding of photon and not assigning basic parameters, mass, and charge to it, even though the processes are manifest? I'm not understanding the question. Autar says, I barely understand half of what you're saying, but it sounds very interesting. I plan on trying to read the book on the assignment. What do you suggest as preliminary besides differential geometry? So that's always a problem. It depends what you are interested in. So if you're interested in classical mechanics, yes, differential geometry is interesting, but probably more important is the understanding of classical Hamiltonian mechanics and Lagrangian mechanics and all that. And the good thing about all of these things that seem very complicated, but most of the time, what you really need is a good understanding of the basic definitions. Because whenever you, for example, let's say that you're studying classical mechanics, you're doing advanced mechanics, right? Most of the class is going to be solving different problems. And the exam is solving different problems, might be easy or hard to solve. We actually care of the thing, that it's below. It's like justifying the equations, right? That's basically what we need. And uh, and so for every class, you don't need the full class. You just need the beginning 10, 15% that tells you what the definitions are, and then having a clear idea of how those definition works. So even for differential geometry, what is important is knowing what a manifold is, knowing what a differentiable structure is, know the standard definition of vectors and one forms and some of how these pieces fit. But you don't need to know how all the techniques to solve different problems or integrate different equations and so on. It's just a matter of understanding what the definitions are. And a lot of the time can be done as a consequence. So let's say you start reading a chapter of the assumptions of physics and you bump into the entropy. Have you never seen what the entropy is? Then you can sidetrack and dig and see what the entropy is. And once you have a good understanding, you can come back. You should keep in mind that 90% of the stuff that I know in math, it has been like that. So I studied physics and I studied engineering. Nobody told me exactly what a topology was. I started digging out for things, and I see that there are these topologies, and then I go and learn what I need for the topology, and then I come back. I was doing a probability theory, and then I audited a class that tells me that probability theory, there are measures and sigma algebras, and the class in probability theory just assumed that everybody, of course, knew what a sigma algebra was. And so I started taking, going around and learning what a sigma algebra was, how it was used. So that's how I've been working, and I've been able to go forward. So I don't think that you have to, invest months before you can do anything. But you should dig when there are things that you don't know what they are. And I think that's the problem. The majority of the problems that I see in people working on the foundation of physics is that they don't dig. So there are people working on generalized probability theory that, stochastic hidden variable interpretation of quantum mechanics that haven't looked at what a sigma algebra is, what Kolmogorov probability is, and how they work, how stochastic processes work, and all that, right? That's what you should not be doing. Like, oh yeah, I don't care about those details, right? No, you need to care about those details. But when you get to those details and how, it's basically up to you. Okay, so I should repeat the question. My interest is mostly towards the foundation of quantum mechanics. I'm studying a master in physical physics and work. So for quantum mechanics, I would strongly recommend that you get ideas of linear algebra clear in your mind so that you know what eigenvectors and eigenfunctions, and all of that, how it works. Get a good understanding of what Hilbert spaces are and what are the problems. And then if you don't know, learn Hamiltonian mechanics, because there are so many things that are so much easier to understand in classical Hamiltonian mechanics that work the same way in quantum mechanics that you just just get much better intuition for everything. And another comment, thank you for making the research so much more accessible. Well, thank you for, looking at all of this, because the fact that I make it accessible doesn't mean that other people are going to come here and be interested in learning it anyway. So. Okay. So at this point, since we're at the end, even if there are no questions on this section, there are more general questions about the project, feel free to ask whatever you want. Oh, questions appeared in Zoom. Apart from the Assumptions of Physics textbook, do you know of any other reference in theoretical physics bibliography presenting things in a similar direction? Unfortunately, no. That's the problem. That's why we started this whole project, because I couldn't find the whole thing basically started because I wanted to understand things in this way, and I couldn't find resources. Even the fact that we don't have, that I had to go and figure out what the Lagrangian is, what the action principle is. It tells you that it's not what people typically do, and there might be insights that people have that might be useful that are scattered in different books. So even that I'm interested to know. Like if somebody tells me, oh, there is this book that actually explains this little thing in a way that it's very compatible that you could use, please do tell me. Question from the chat, how can we join the Discord server or be involved in the research? Should we work on the problem first and send you a preliminary report? I'd rather first that we have the discussion. So if you join the Discord server, you can basically propose and say, oh, I want to look more at this problem and I want to understand what are the issues. Then we can have we can schedule a live discussion. And there are likely other people that might be tangentially interested, or they've already done something. And this is the problem. If people start working on the problem first and they're not aware that there are other people that are already thinking about that, it's just wasted effort. In fact, ideally, what we would like to have is groups of 2 or 3 people that are working independently on some project, that they know each other, that they know what they're doing, and then from time to time they report to the group and saying, oh, these are the things that we've done, these are some results that we've had, and these are the things that can be these are done, and these are still open idea. This is ideally how this project should work. My dream would be that in 3 years, in 5 years, we have something like that, different people around the world that work. And for joining the Discord server, just send me an email or an email to info@assumptionofphysics.org saying who you are. I'll send you an invite, and then you join the Discord server. And please use your real name so that I can correlate discussions on the Discord server to real people and email in real life. Okay, now question on Zoom regarding the problem in classical mechanics. What level of Hamiltonian Lagrangian mechanics is required? Because some books provide very advanced treatment, like Arnold and Jose Saletlan. So I basically reverse engineered Arnold and Jose Saletlan. Like I started with those things. The problem was that it was very mathematical and I couldn't understand a thing of what they were saying. And so, because again, it's in this language of differential geometry where vectors are derivations and all that. And then I basically started making a translation map. So everything that you learn from those things are good if you can digest them. But the goal would be to write a book that is sort of that says the same things, but we can actually draw picture and have a good understanding of what those things mean physically. Right. So the reverse engineering of the principle of least action actually came because I was reading Arnold, and I was looking at some of the things that he was doing, and I could understand mathematically, but I didn't understand what is it that they meant. Once I started to understand what they meant physically, I was able to actually find a shortcut of results that made more sense and actually gave you the physics much in a much cleaner way. Uh, so you can basically say, I want to learn the full differential geometrical treatment, which then you could also help me sort of bridge, like what I don't have right now that could be interesting to do if somebody already knows it in the advanced way, what is the translation dictionary from that more advanced framework to what we have, because I've been concentrating in somebody has done classical and classical mechanics in a sort of in the more physicsy way where you have the equation and you futz around with them. And so I devised the current version of reverse physics in that way, so that it uses that. We could have some version of the conditions that are more specified in a sort of more standard differential geometric way, so that things are more intuitive for those people, and again, so that everything can match. So I hope I answered the question. I said a lot of things. I think there was that answer in the way. And then a comment from the faculty. I made a final project about your interpretation of the stationary action with the references, of course. I got a 10 for it. Very good. Like that, this actually makes me very happy. Like if that's another contribution that I can give, tell other people that there are these results, such that we can raise awareness and that there is a better way to do these things. Hmm. I'll wait to the usual minute, but again, if you guys have any question on anything about the project, you're welcome to ask at this point. Okay, so I think the queues are emptied. I don't think there are questions coming from either Zoom or YouTube, so we can close it here. Thank you again for everybody for joining. Thanks for those that also have followed on YouTube and they're gonna watch maybe this video later. And again, if you guys want to participate, just send me an email and I'll bid you farewell and see you next time online. Bye. Okay, so